We're looking at a typical force table problem right here. So we're looking from above. We're looking at a force that's acting with a 9 Newton force at 30 degrees from the x-axis. So we're measuring 30 degrees this way. And then we have something else pulling on this area here, 3 newtons in the 290 degree area. So it's 290 degrees all the way this way. What we can do is we can pretend that we're adding these two vectors together. Now, do you see this 3 Newton vector here? I'm going to take it and I'm going to slide it this way, but I'm just going to use a different color. So this is 3 newtons. I mean, effectively, we can get rid of that. So our answer this should be the resultant force, and our answer is going to be the opposite of that in this direction. So if this is 12 newtons here, this is going to be the opposite of 12 there, 12 in the other direction. If this is 10 degrees here, this is going to be 10 degrees over here. A second ago, we took these components and we just added them visually, just head to tail. We moved this vector over here and we added them. Now you could do that with a protractor and with a ruler and get the answer. But more traditionally in class, we've been using SOHCAHTOA to add the vectors together. They should come out exactly the same, so don't forget what we just did. But let's break this down into its component parts. We have a y component here, and we have an x component over here. Now this is going to be hypotenuse sine theta. This is going to be hypotenuse cosine theta. Then over here, we're going to break this into its component parts. This is going to be hypotenuse cosine theta, and this is going to be hypotenuse sine theta. When you do your plug and chug, this vector right here, this component vector, is going to be 4.5 newtons. In other words, it's going to be hypotenuse, which is 9 newtons, sine of 30 degrees. This component is going to be 7.8 newtons after you follow through with hypotenuse cosine theta. Now let's go to the blue vector down here. Its component parts in the y direction. It's going to be hypotenuse sine theta. When you plug the numbers, it's going to be 2.8 newtons. Now don't forget, this angle from here all the way around was 290. So 70 more would give us 360. So this angle would be 70. This angle would be 20. Now we've gone through this. You should be able to do this. So again, we're going to take this angle as 70. So we have hypotenuse, which is 3 newtons, sine of 70 degrees, 2.8. And then for this component right here in the x direction is going to be hypotenuse cosine theta, which is 3 newtons cosine 70 degrees is equal to 1.03 newtons. Don't forget why we broke down those vectors into the component parts is because we can only add vectors mathematically if they are on the x or the y axis. For example, I can add 4.5 and 2.8 because they're both in the up and down direction. I can add 7.8 and 1.03 because they're both on the x-axis. So this is how we add them. I'm going to add 4.05 to 2.8. One thing you can't forget, however, is 2 point is actually negative 2.8 because it's in the downward direction. Everything else, on the other hand, is positive. Positive 103 because it's running in the positive x direction. We're going to say this is positive 7.8 newtons because it's running to the right. And since 4.5, we take this to be upwards, we're going to say that we have positive 4.5. So we simply just add them together. I'm going to change the color here. We're going to go force total in the y direction is equal to positive 4.5 newtons plus negative 2.8 newtons. And then in the x direction here and here, I'm going to add those two numbers. So we have force total in the x direction is equal to positive 7.8 newtons plus positive 1.03 newtons. So our resultant answer is going to be 1.7 newtons in the y direction and 8.83 newtons in the x direction, positive x direction. So let's redraw those vectors. We have 1.7 newtons in the y direction. Now you got to add them head to tail. So this is going to be 8.83 newtons in this direction. So the answer to our problem is this vector that's dotted. So what is this answer here? This is the Pythagorean theorem. This is our answer. So to find that answer, use the Pythagorean theorem. And that's simply square root of 1.7 newtons squared plus 8.83 newtons squared. This force total is equal to 8.99, or let's just call it 9.0 newtons. Next big question is, what angle to the x-axis is this? Let's draw xy axis. Okay, so looking at this, what is the angle to the x-axis? You can choose this angle here, or you can choose this angle here. I don't care which angle you go after. The beauty of maybe choosing this angle here, which you're going to say it's let's say 85 degrees east of the north axis. The nice thing about choosing this particular angle is you already have the adjacent leg and you already have the opposite leg. If you're going to do this angle here, take this vector and physically move it over here. It does the same thing. Okay, in this case, the opposite would be 1.7, and the adjacent would be this vector over here moved down here. I'm going to solve this angle here. It's just traditionally what I do. I don't care if you solve for this angle here. So we have tangent -1 opposite or adjacent. Now don't forget, this 1.7 can be drawn over here. So that's the opposite, so that will be 1.7. And then this part of this triangle that will be made here, this is going to be 8.83 newtons. So you're just taking this vector and sliding it down. Vectors can be manipulated. We've talked about that in the past. So our answer is going to be, this is theta. Theta is equal to, this will be 10.9 degrees. So the resultant vector is 9.0 newtons. Our angle is 10.9 degrees. But our answer is, this is what, don't forget, this is what the two forces added together equal. We want to know how much in this direction do we have to pull to counteract this total force. So it's simply 9.0 newtons in the opposite direction, and this angle here would be 10.9 10.9 degrees. You have to be descriptive when you say 10.9 degrees. Well, 10.9 degrees from where? You can say 10.9 degrees, and if this is the west axis, you say 10.9 south of the west axis. Or you can measure it all the way around here. This would be 180. This would be 190.9 degrees. So you can say 190.9 degrees if you want to. But if you're saying that, again, you're measuring it all the way this way. Traditionally in class, what we've said is 10.9 degrees right here, and you'd say south of the west axis.